Good day. My name is Matthias Goebel. I'm working for Embedded Brains, and I'm going to present you today on space qualification for the open source real-time multicore as RTEMS. Let me first get you a brief introduction on the Embedded Brains. We're a small company, about 15 employees, funded about 15 years ago, and we are specialized on hard and software engineering for high-performance systems in the aerospace, automotive, and industrial automation domains mainly. And we are the main RTEMS developer and supporter in Europe, what is basically half of our business. For this presentation, I'm going to present you a short introduction to RTEMS SMP, then looking what's new with respect to qualification. And this is the fact that RTEMS is an open source software that is quite a different thing for qualification. What we have introduced here is a very far-reaching automated documentation generation and testing for the qualification. Then I'm going to explain a little bit how does it work with the concept, the process, and its deliveries, and giving you the outlook where we are and where we intend to be in the next future. RTEMS SMP has been coming up from RTEMS, which itself is established in the 1990s, quite a long-standing systems in the single-core version. The SMP version was developed since 2015 so it's about 5 years ago, and has been introduced in different steps in the recent years. The SMP, the symmetric multiprocessing, that's the multi-core version. Specific features is that this is a multi-core OS that requires just about 50 kilobytes of memory, what is quite runs on a very small system as a multi-core system. It has a scalable timer and support, fine-grained locking, so the big kernel lock is removed. We have locking protocols for mutual exclusion, priority sealing, different options. But there is also an important limitation with the current RTEMS that we have no memory protection. We have quite a few BSPs supporting SMP. Meanwhile, the Spark GR712C and the GR740, some Power PCs from QRIQ with 1 to 24 cores running with SMP on RTEMS. We have different ARM processors, and we have a BSP for the RISC-V. So that's quite well established so far. What's missing is that for application in space, we have only a very outdated single-core versions of RTEMS available, different sources, but the SMP multi-core version is not has not yet been qualified, and this is the topic of this presentation. This is not only a simple qualification that we run here because we have the open source software, and we have some different experience with this open source software. As typical, we have open source software is maintained by a community of volunteers. That's the case of RTEMS. So we have many configurations, many patches, many updates. So this is a quite very dynamic system. All people looking into the repositories will can follow up with that. Looking at the qualification process, this is normally a very laborious intensive process that can be far more labor intensive than the development of a software itself or the core code writing. This is not only laboring process, it also has to be integrally performed for a set software package, because the tests and all that runs with the software. So you can't qualify piece by piece nice separately, but the whole package. And with RTEMS, it's even more labor intensive as the application software has to run with that together. So this is normally quite static process. And we have made the experience in the past that some qualifications of the single core version were performed with private branched off versions. So they took the community version of RTEMS, the mainline, and then developed it from there, a qualified private version. But the problem is that it turned out to be impossible to update or extend updated versions. So from that point on, you had to take all updates and implement it on your own branched off version, what is quite impossible, even though the RTEMS system is rather a small software package. So after a few years, the technology was quite outdated and the maintenance effort increased exponentially. Like Corona cases sometimes. So at the bottom line, those versions couldn't be maintained anymore. And we wouldn't do the same, have the same experience again with the SMP qualification. So we chosen a bit of a different approach. This approach is that we first are striving for the alignment with the RTEMS community. The code for qualification is based on the RTEMS mainline, and it shall remain based on the RTEMS mainline. And the tool and test suite should be aligned with the RTEMS community. This is a process. This is still in process because it's a main development currently that needs to be integrated with the community. But we consider it being quite important that the community has the integral control, and it's a public version here at that point. In order to obtain that and keep it alive, we need a most flexible and efficient qualification process because the open source software is quite dynamic and we won't branch it off. So we have developed a quite extensive automated testing and document generation as far as possible. And we were lucky to have some initial funding by ESA that allows us to enable a quite low threshold start by this initial funding. So we have to get a good starting point. The objectives of this project was to have a pre-qualification for ECSS, that's the European standard qualification standard for category C and D, to get it started for some selected configuration. We wanted to have some verification evidence for RTEMS and its selection of libraries. So you see there's some selection on it. That's not the whole RTEMS project. We have to get started with a kind of what we call space profile. We want to produce validation evidence to demonstrate that all the requirements are met, and give some guidance how to replicate the use result for a full qualification. The restriction, I mentioned it, RTEMS has no memory protection, so that we can only provide an OS that is pre-qualified, and the final qualification has to be obtained together for OS and the application software. Funding was done by ESA, I mentioned it, with some national partner organizations for the last 3 years, and the project has been completed just now a few weeks ago. So let's have a look on how does that work in the real environment. The request of the dynamic process and static aspects of qualification can be shown what needs to be done if we change a snippet of code only. We have to produce a lot of change documents to change the design, the requirements, the tests, and the software, of course. That's the course. We have to check that we can reach code coverage, run the static code analyzers, and recreate the matrices. After that is done, we have to change all qualification documents, or most qualification documents, the traceability metrics, the test description, test results, coverage information, the analyzer reports, etc. And finally, that has to be processed to recheck the ECSS, the standard conformity. So that's a quite huge process that has to be basically processed for any change of code. This works only if we do that quite automatically. And this is the concept we've worked out for that. We start with a large number of specification items that that have been created manually, and this is fed into a tool chain that is written in Python forms of Python scripts that read in the YAML files. And from the toolchain, we create directly the output documents with respect to requirements, etc. And we run the validation tests that are written in C code and reprocess the results to create output documents. A little bit more in detail, that looks like a build system that we come in with a configuration, download the sources from GitLab, split qualified and not qualified code, compile and install the software. And then the core in qualification starts with the run the static code analyzers, execute the tests on the simulator and on hardware, run the coverage analysis, fill the results and analysis in documents and different docs, generate those documents. I'm going to explain that right now, and then put that all in a zipped document that represents the QDF together with some manual files. So that's the process, how it runs. In fact, it is a little bit more complicated to create all those documents. I'm just explaining that at the example of the document generation, where we get all that together. So we look at the configuration, the build logs, the test results, the coverage files, static analyzer, and different inputs after the whole toolchain has been running. We analyze those inputs, generate text snippets, combine that, those snippets with each other and with the manual written documents. And then we create the document sources that is then in Sphinx format, Sphinx created into HTML and PDF documents. That is run more or less automatically. You've seen we have some manual written documents. I'm going to explain that later on. We use quite different technologies on that. Of course, we have, if you look at the list here, we have a lot of standard build system aspects. We currently run it on Debian 10, use Python 3 for the qualification toolchain, use PyTest, C assembler and WAF as a build system, GCC and the RTEMS framework. We use YAML for configuration files, Doxygen for source code documentation and tags, Sphinx and LaTeX for the document generation, and then we work with Git, Coverity, CPP check for the code analysis and the CLang, and GCGCOV and GCOV are for coverage analyzer and metrics for code metrics analysis. We provide some verification activities. We use the static code checkers as mentioned from Coverity, CLang and CPP check. We do product and process matrices, assessment of testing and validation activities, and we do problem and non-conformance reports. We reach with these tests currently a code and branch coverage, which is 100%. That is more than category C and D will require, but we aim for category B and possibly for category A at a later stage with using the same technology. So that goes currently a little bit beyond what is required for the current qualification. We generate a couple of QDP documents automatically. You see a quite vast list on the left side here in the slide. I'm not going through all that. You might watch it on yourself. We have, of course, a lot of manually written files that are the framing aspects for the software reuse, the software review, the configuration, and the development plan. They are integrated automatically together with some other information and some formal verification aspects, and a few documents are not part of the QDP itself, but are part of this documentation set as a whole. Of course, after this huge automation, which allows to run the qualification in a few hours formally, at least to produce the second few hours. Then we have some manual work remaining. Changed requirements needs to be introduced manually, of course. Problem reports needs to be analyzed manually. We have to code checker issues to fix that manually. And we have to consider that certain ECSS clauses cannot be checked automatically. So a little bit of manual work still remains. And of course, the toolchain itself must be maintained for changes of code, changes of functions, etc. But what we can achieve is that we have a significant less effort through this automation, and this allows to rather easily adapt to newest RTEMS version, to include more API functions, to include more device drivers, and also to run qualifications for different processor architectures and boards. How does that work in practical, from a practical side? We have this RTEMS SMP qualification data package that can be downloaded from the ESA website in the next few days. That includes all the documents, the test suite, the tool chain, and the example cases. This is configured for the Leon 3 and Leon 4 processor currently. And it has the API subset according to the space profile. That's also listed in the configuration, software configuration file with all the details, what's included or not. This can run as a pre-qualification for RTEMS that shows how it works. And this has been approved by ESA so far. This can be used together with the application software that needs to be qualified, of course, for a final qualification. Reason for that is that we have no protected memory in RTEMS, so the final qualification has to be done in conjunction with the application software and the operating system. Let me devote a few seconds also to this aspect of open source. We have the source code open from RTEMS. This is an open source system, of course, and we have now with this qualification package also being open to the public, quite an open source system that extends the qualification. But just to give you a few aspects that need to be considered when working with that, you know about the positives of open source. I don't think that I need to devote too much time on that. There are no royalties. It's easy getting started without bureaucracy. It's 100% transparent source code, and there's no obligation to update to a code according to suppliers' plans. So that's quite easy in handling, and this is makes open source software quite popular. But also we have to be aware, or you have to be aware about the risks using open source software. Often it is underestimated, the resources are underestimated that are required for getting into existing code. That's quite a huge code package, the RTEMS code itself, and particularly the qualification system or the qualification toolchain. So it takes some time to adapt to that or to create new functions in such an environment. It is quite risky to create a private version. I mentioned it in the earlier phase of this presentation that earlier or later this will be outdated, and keeping updated a private version is quite impossible. Even for larger companies, it turned out it wouldn't work properly. And one needs to keep updated with all the many developments in the community version. So this is quite a dynamic process, and this takes some effort. So our experience working as professional expert services, that it can be more efficient to work with experts than all doing it by yourself. So this is the part where we can introduce embedded brains or OIR as possible partners, or may suggest embedded brains and OIR as possible partners to that. If you don't want to do it by yourself, or consider it's too labor extensive for this specialized type of work. The outlook of this project is that we currently have this qualification toolkit for the Leon 3 and Leon 4 processor with a subset and interfaces according to the space profile that's available to the public. The independent software verification and validation process for category B qualification is in process. That's a separate project that will run in 2022 now. What is still outstanding are the QDPs for other controllers. We can anticipate Dahlia, various AMR cores where the BSPs are available. And we have the RISC-V where also the BSP is all available so far. We anticipate further interfaces and drivers. The POSIX, for POSIX IP, OpenMP, some high-level drivers are still missing, and the lightweight IP stack to be done in the next future. To conclude, RTEMS provides an attractive option for long-standing open source real-time operating system. The SMP extends functionality for high-performance multi-core systems such as the Spark systems, the Zynq, Dahlia, and RISC-V processors. The SMP qualification now adds a framework for automated testing in order to facilitate the European space qualification. And now this provides a low threshold entry to qualification. On the basis of this framework, new qualifications for other controllers and interfaces can now be realized most economically. Thank you very much for your attention, and I'm happy to respond to questions. You see the contact data here where you can get further information and contact Embedded Brains. Thank you very much.